All right. So concentration, you have seen the effect of concentration on equilibrium. Now we're gonna go to the pressure and volume. Okay. So go back to the very similar equilibrium. Nitrogen react with hydrogen gas to make ammonia. All right. So let's say we have 4 moles of gas. So on this guy right here, and then 2 moles of gas on the right side. So what would happen if we double the pressure? Okay, let's see what happened. So if we double the pressure, we adding pressure onto it, the equilibrium will feel like, wow, we have way too much pressure right now. So go back here. Right now we have some pressure, all right? And then adding the pressure, equilibrium will feel like, oh my God, we have too much pressure right now. This is stress. We have to relieve this pressure, right? Too much pressure in here. The equilibrium, we have 2 options, either shift to the product or shift back to the reactant. What do you think it will do? 2 moles of gas on the right, 4 moles of gas on the left. Well, basic logic. Too much pressure right now. Are you going to produce more gas? No, we were going to produce more gas right here. So too much pressure, we have to get rid of the gas. So to keep the pressure the same, so we have to lower the pressure. By shifting backward doesn't help you making more gases. So 4 moles of gas going to be produced if you shift backward. But if you shift forward, only 2 moles of gas is produced, right? And we can get rid of 4 moles of gas to make 2. So that's lower, and will be lower in pressure. So in this case, too much pressure, the equilibrium of gas is going to go shift forward. So shift forward, I'll take a look right here. So take a look at what happened. So to more nitrogen gas and hydrogen gas will combine and make more ammonia. So basically the whole, there will be a lower amount of gas in the system. Okay, so basically lower the pressure. So basically the equilibrium try to maintain the pressure. Too much pressure inside. Well, can we release the pressure? Can we lower the pressure? Okay, now let's increase the volume. So go backward. All right, so we can increase the volume. All right, increase the volume. The equilibrium realize that, well, looks like we have way too low pressure. What are we gonna do? Well, we have to make more gases to make more pressure, to increase the pressure. So try to stay, basically, equilibrium try to keep the pressure the same, whatever we do with it. Okay, so low pressure right now. Well, let's make more pressure by shifting backward, make more the reactant. So take a look right here. So 2 of ammonia gonna break apart to make more nitrogen gas and hydrogen gas. Okay, that's the effect of the pressure. All right. Now there's some tricky part about it. So let's say right here, let's look at the equilibrium first. In this, go back to this one. So there are 4 moles of gas in the reactant side and 2 moles in the product, right? But in this case, the mole of gas in the reactant side and the product side are the same, right? Which means that whatever you do, if you increase the concentration, take a look. So if you do KC right here, so I just plug in, I'm going to get that number 0.5. Okay. So if I increase the increase the pressure, right? Increase the pressure. Well, what's going to happen? Everything will double. Look at the math first, right? Everything will double. So double, everything double. So 1 to 2, 2 to 4, 1 to 2, because we have lower the volume. So concentration is double. And the new K, if you do the calculation, plug in 2 to the second and 2 and 4 at the bottom, cancel out, 0.5. Nothing changed. My point is, if there's no change in moles between of gas between the reactant and the product, either you add more pressure, release pressure, no effect on the equilibrium. Doesn't do anything. Okay. All right. Another way. So another one. So now, this time we increase pressure by adding the other gases into the system. In this case, we do argon. Right. So argon is stable. It's inert gas. Doesn't do a reaction with anything. So we make sure there's no reaction in there. So anyway, so we add argon in there. Of course, the pressure inside going to be higher. Right. But what's going to happen? Well, nothing's going to happen. Let's take a look at the mathematical explanation, right? So Kc of this equation still the same. So a product square over reactant is cube, hydrogen is cube. Okay. If you add argon gas in this container, of course the pressure goes up, but the concentration of all these doesn't change, right? Concentration is mole per volume. same moles of hydrogen gas, same mole of ammonia, same mole of nitrogen gas, same volume with the same container, nothing changed. Concentration doesn't change. Kc is still the same, no effect on the equilibrium if you add some other gas into it. Look at the Kp. Some people, oh, wait, hold on, the pressure changed though. I'll show you. The partial pressure of ammonia, so can be calculated as P equal to nRT over V, so PV, so move V down here, all right? Mole is the same. Volume still the same container, you know? Temperature the same, we don't change the temperature. R is a constant, nothing changed. The partial pressure of ammonia doesn't change. The partial pressure of nitrogen doesn't change. The partial pressure of hydrogen doesn't change. Only change is the partial pressure of argon, but argon doesn't affect anything on here. So, increase the temperature, increase the pressure by adding other gases does not affect the gas equilibrium. That's my point. Okay, quite kind of long explanation, but that's what I mean. All right, right here. So carbonated beverage, blah 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 blah. So we have so this is how they make soda. So they carbon dioxide is not soluble in water. So carbon dioxide is non-polar. If you remember that, adding to water is highly polar. Not gonna go well. So carbon dioxide in water is carbon dioxide is not soluble in water. That's my point. Okay. So this equilibrium is actually go backward, right? But we can force it. We can force carbon dioxide to dissolve in water by adding a lot of pressure. Okay. So the question asks, after the soda pop is open, the carbon dioxide escapes. How does removing the carbon dioxide affect the concentration of carbonic acid in this soda? All right. So before open, right? So the high pressure inside, so we try to make carbon dioxide dissolve in water. So we kind of force it to go in the water. So add a lot of pressure in it, right? When you open the cap, right, the soda cap, the pressure is lower, much lower. Okay, so we release the pressure. Basically, the pressure of the system is lower. Now, what does equilibrium have to do when the pressure is lower? We like, pressure is lower. We have to maintain the pressure. What does it do? Well, it has to shift to the side that makes more gas. Does it make sense? Right? Any gas here? Well, only carbon dioxide is a gas in this equilibrium. Right? So in this case, this equilibrium has to shift backward, make more carbon dioxide. And to make more carbon dioxide, what happened to the concentration of carbonic acid? Lower carbonic acid. So, right, when you open the soda cap, you probably have heard the noise like, psst, right? You heard that, right? It's fizzy, right? That's because of carbon dioxide rushing out. Equilibrium even make more carbon dioxide. Carbon dioxide keep rushing out from the cap, and that's why you hear the noise piss on it. That's the explanation. Okay. All right. One more time. So does the number of products increase, decrease, or remain the same when each of the following equilibrium is subject to a decrease in pressure by increasing volume? Okay. So decrease the pressure. All right. First one, decrease the pressure. The equilibrium have to make more gas by shifting. Well, okay, 2 more shifting forward. All right. Now the second one. The second one, the gas is only on the left side. To make more gas, this guy have to shift backward. And the last one, okay, we have gas here and gas there. 4 moles and 4 moles. Well, remain the same, right? This case remain the same because nothing gonna change. Shift to the right, same gas. Shift back, same amount of gas. So nothing change, does not affect this equilibrium. Okay. All right, move to the last factor that affect the equilibrium. That's the temperature.